Hey, everybody. Welcome to our virtual organic symposium for today. I am your co-host, Carl Hansen, and I'm joined here with my co-host, Steve Silverman.
Hey, Carl.
How you been, Steve? What's going on? How are things
Pretty
going?
good. Pretty
Yeah.
good. Starting to get back into going back to work, things like that.
So things are getting operational. That's good. That's
Yeah.
good.
No.
I couldn't help but notice, Steve, your hair's starting. My hair's getting really long. Like, you've been quarantined
Yep.
when your hair's getting long, and you usually keep it pretty high and tight, but even you are looking a little hippie-ish there.
This point, I'm pretty much ready to travel to a different state to get a haircut.
Okay, all right. Yeah, you're deeply ensconced in New Jersey, where things are pretty locked down. So yeah, I hope everybody out there everybody's been staying safe and coping with all of this. I know everybody's conditions are things are pretty local, but it's great for all of you who could join. We're really glad to have you, and we've got another installment. We've been doing these monthly, and setting them up monthly so that people can keep connected and still see science and all that good stuff while you're adjusting to the new normal. So today we have Matt Bio from Snapdragon Chemistry. He's the CEO there, and Tehshik Yoon from Wisconsin Madison. I'm glad to have these guys on board for today. We'll get into the introductions in a minute. Steve and I are going to do a few announcements like we always do. So let's just kind of roll with it. Just as a preface, these are brought to you by the Division of Organic Chemistry, as well as the Center for CH Functionalization, Selective CH Functionalization. And importantly, Emory University graciously allows us to use one of their webinar webcast type Zoom channels to facilitate this. Two people there, Rio Fabrian and Denise Bale, are really instrumental. Those are people behind the scenes to help make these things happen, as well as other people from the CCHF and the DOC. So, and just before we get into it, because I always forget, you can actually submit questions through the Q&A button. And we'll as we go through, we'll try and get to as many of those as we can at the end of the talks. And then if there's questions left over, we'll see what we can do about getting those answered and out to all of you. Next slide, Rio. Yeah, so just to talk about schedule, there's a couple events coming up for the CCHF at the end of June. They have another event with Pedro Perez, Ang Lee, and Rob Knowles. And then in September, in middle of September, there's one as well. Most of you who get the announcements for this are probably getting those announcements for the CCHF. We have filled out our schedule for, through October. Maybe Steve, you could walk through what we've got on tap for the DOC.
Sure. So, as I think everybody knows, because of the COVID situation, we wanted to add a number of these. So we added them monthly through July. We may get back to a fairly normal schedule after that, or we may add in a few more depending on how things go with the ACS meeting, things like that. So in June we have Professor Vidong from UC Irvine and Andy Evans from Queen's University. In July, Alison Wendlandt from MIT and Eric Voigt from AbbVie. And then in October, Nuno Mal from the University of Vienna and Neil Gard from UCLA. Stay tuned. There will likely be some additional.
Yeah, I think we'll see what we can do to maybe add one or two more if we have available spots, times to do it. But I think the other thing too is if there's, I think we try and cast ourselves as accessible, Steve, right? Like, please tell us what you want, and we'll work to bring it to you, right? We aim to please the organic.
We're both pretty active on Twitter, so feel free.
Yeah. So we'll give you our Twitter handles at the end. So what's the next slide got on it? All right. Oh yeah, and maybe you could tell Steve, what's this? Did you want to give I don't know whether you wanted to give like we had a slide on, but I think you want to just give a status update. Like we're kind of in limbo still with the ACS in August. That's a big event for us at the DOC, right?
Yeah. So yeah, obviously that's the ACS meetings are pretty much our biggest events of the year. Unfortunately, with San Francisco, we're still in about the same situation we were in last time. What we can tell you is that we know the meeting is going to happen. We know that it will have a virtual component. We don't know what that virtual component will be relative to the live component. It'll probably be mostly, if not completely, virtual. But right now, we don't have a full update on that. So hopefully, by our next virtual symposium, we'll be able to give you a little more clarity on that. Regardless, the program is coming together nicely. We have several hundred abstracts submitted, so we are looking forward to that meeting.
And in the meantime, you can go to the DOC website, and I think all the content is open still, right?
Yes, until the end of the year.
Yeah. So if you haven't already, I would encourage you all to check out the DOC website. This website's maintained by Brian Myers and Joe Ward, who are part of the DOC executive board. I think they're looking for somebody to help them. Like if you're an aspiring webmaster, I think they're looking for another accomplice. But it's got lots of great content on it, a lot of great talks. All of those you can stream. You can even stream these. I recommend you go past the introduction. You go straight to the talks. Don't revisit any of the introductions of these. But this is a resource that we've opened up for everybody, and so please check it out. I think we talked in the past. If you go to the next slide, Rio, we've talked in the past, like the number one. There's actually a lot of resources for organic chemists. A lot of things like we've talked about the solvents in the past. There's informational stuff. It connects a lot of things that are have been all over the web in a central place. So these guys work pretty hard to have these resources for you all. One resource, the most hit one, at least when we last checked, was the solvents. But one resource we talked about last time was the organic links, which is on the next slide. Organic links is our, so organic links is basically a compilation of every organic group in the United States, right, Steve?
Yep. Right now, just the United States.
If you go back, Rio,
international.
Yeah. So this is actually, there's a group of folks on the right who work on maintaining this, and you could go and basically search for research groups by state. But there's a new feature on organic links that I just learned about, which is a you can basically submit in a comments if you're looking for, I think if you're looking for a postdoc, if you sort of have an open position for a postdoc. So if you click once, Rio, and I love this fancy animation on this one. Yeah, just click to the next slide.
You're a PI and looking for a postdoc.
Yeah, you could basically submit a form and you can say, I would like to advertise a postdoc position. So what they want to be able to do is create a place where folks can find, get connected with PIs that they would like to do a postdoc for. So kind of cool. If you, and you can contact the board, like if you do organic chemistry, or like maybe you're on the fringe between organic and cross-discipline fringe, but you consider yourself, an organic lab and you want to be on the list, I think, just go to the form, submit it, and I'm sure they'd be happy to add you. I don't think there's any like really hard litmus test for whether you're an organic chemist, although we probably could think one up, right, Steve?
I think we could.
So last time we were talking about solvents. We had a lot of great solvent tweets, right? And then last time we were talking about oxidants. And, I think we tried, I don't know whether it's because we got a little political, but I sort of made the comment like, about, I like bleach. Bleach is my favorite oxidant. It has been for a long time. And so, we asked for everybody to submit on Twitter. We thought we would get this overwhelming avalanche of, we said, give us your favorite oxidant. And, Steve and I have this running joke where he's like, people actually don't feel that passionately about chemicals, Carl, or something, something to that effect. You're kind of like, at least that's what I think you think, right? Like, I don't know if anybody feels that strongly about
you maybe at the higher end of the nerdiness spectrum than the rest of us, Carl.
Yeah, maybe I am, but we got a few, like Donna Heron. If you don't know Donna, she's great, but we got a few. We got Donna Heron piped in about one. A couple people did. in Brio, you're going too fast, man. There's some drama here on our top. You know, you're stealing the thunder here. So you know, in lieu of the tweets, the copious tweets that didn't happen, I did extensive research. Steve and I went to the web and we found the top 5 oxidants of all time. Okay, these are the top 5. Actually, they're the top 5. So the 5th one is sodium carbonate hydrogen peroxide complex. It gets the tough stains out. You know why it gets the tough stains out, Steve?
No, why, Carl?
Because that's the active ingredient in OxyClean. I don't know if anybody else. OxyClean's great. It's a great product, and I still, like, honestly, when I found this one, I was like, is it a salt? Is it a complex? I mean, you know what I mean? Like a little pKa thing. When we've talked about pKa stuff before, but that was number 5. Number 4, the Swern oxidation. Success you can smell. Anyone who's had the pure pleasure of running a Swern knows how much it irritates all of your lab mates, and how you try and work it out of any large scale process, right? Like nobody likes this, you know, the smell of the Swern, but it works, right? Next one. Yeah, ruthenium tetroxide, sodium periodate. Well, how do you feel about that one, Steve?
It's a good one. I've definitely used it quite a few times.
Light your campfire with a flamethrower. You know, that is like the most energetic reaction. It's like one of the most energetic reactions I think you can run, sodium. And if you've ever run it, you know it, you remember it. Like it's sort of, you know, thermally and visually fantastic. So, and it'll
nice volcanoes.
Yeah, anything that takes an olefin into, you know, it's almost indiscriminately off of a molecule is got to be okay. Number 2, potassium permanganate. This is one of the ones that we got a lot of tweets about. Taste the rainbow, feel the rainbow. Love it. You know, it makes all the colors. I didn't know this, but potassium permanganate is like one of the World Health Organization's list of like safest, most essential medicines, right? So, you know, it's used for like a topical anti-infective, among other things, which I thought was kind of cool. It's been around since like 1650. Somebody invented potassium permanganate back in 1650, believe it or not. And then number 1, what do you think number 1 is, Steve? Rio, I think advanced. What do you think number 1 is?
Well, what's the most atom economical oxidant?
Yeah, it's got to be oxygen. You know what? 4 out of 5 mitochondria choose oxygen for what they need to do and oxidize every day. So that's number 1. Sadly, I don't think chemists like to use it that much, right? It's kind of underserved. At any rate, so those are the top 5 oxidants revealed to all of you. If you feel strongly about this and you feel like we left something out, you can tweet us at Carl the Chemist or at ASYMTMM. Steve's even dorkier handle than my dorky handle. And let us know what you think. And we will be happy to share anything. We will curate whatever's good and maybe share it on our next webcast. So with that, I'm going to introduce our first speaker, who I've actually known Matt for a really long time. So Matt is the CEO of Snapdragon Chemistry. I met Matt. Matt did his undergraduate. Matt had like an industrial job, like before he got his PhD, right? Did his undergraduate work at Muhlenberg, right?
Yep.
And then went to Columbia and did a PhD there with Jim Layton, and that's how I know Matt. How I first met Matt, because Jim and I were lab mates long time ago. And then Matt joined Merck Process, which is where we overlapped, and we were actually lab mates for a number of years there. And Matt used to be a chef, right, Matt?
Yes, indeed.
And so we would inevitably talk about food, and we were both early guys. Matt was always at the lab first, working before I even showed up. But we would talk about food in the mornings and get so hungry, like we would both like run into our office and eat our lunch at like 10:30. But you know, the restaurant thing, like Matt had, you know, always had his station set up and was
mise en place, right?
Exactly. Matt was at Merck for a while. He was in Rahway. He also was in England, and then he came to Amgen and he worked at Amgen. Him and I worked really closely at Amgen for a number of years, and where he was a lead as well as had a team on development programs. And you know, I think Matt, throughout that whole part of his large pharma experience brought a lot of chemistry innovation, and fundamentally just gets down to the bottom of why things are happening and how to make processes more efficient. And so at a certain point, Matt decided that he wanted to go off and start his own, be off and be part of a company that was solely focused on chemistry. And he joined Snapdragon. I think you were sort of employee like number 1 or 2, like you were pretty early on.
Two.
Yeah,
I think so. 3 or something, maybe, I don't know.
Yeah, and Snapdragon, Matt is going to talk about Snapdragon, but essentially Snapdragon is all built around developing continuous flow chemistry and continuous processing options, as well as just doing good chemistry, right? To be fair.
I hope.
Yeah, of course. So with that, Matt, I'll turn it over to you, and you can go through your talk.
Okay, great. Thanks, Carl. Thanks, Steve. Yeah, it was a real pleasure to share the lab space with Carl, and that's where I learned his favorite solvent is acetic acid. And I can tell you that memory has served me well on many cases. So let me just share this. So hopefully I am sharing the screen. Can you see that?
Yep, we got it, Matt.
Great. So what I'd like to tell you about today is actually
on the screen though.
What's that?
You're on the presenter view right now.
You got to swap views, Matt. You know how to do that up at the top?
Let's see. How do you do it up at the top?
There's usually a setting. I think if you're in PowerPoint, there's a setting at the top bar, and you can swap views. So it says swap display. It's got that little, yeah, there you go, man. And then, yeah, perfect. Awesome.
All right. Okay, so what I'd like to tell you today about is an internal research project that we had, and it really was focused on ring closing metathesis and how we could make this work in a continuous system. And we are going to use pervaporation technology, which is something that frankly I didn't even know about until about 5 years ago when I was introduced to it by some folks at Compact Membrane Systems, specifically Hannah Miernan. She's the CSO down at Compact Membrane Systems, and they focus on the development of pervaporation membranes. And I'll give you some more details about what those are and how they work in the talk. This project brought together a very talented postdoc or a graduate student in Tim Jamison's lab, Chris Breen. He's at MIT, brought him into our lab to work with us and Compact Membrane Systems to make this project happen. So a little bit about why we would be interested in these things. Snapdragon's mission, its founding statement really was to deliver better chemistry. And we're doing that through a combination of first principle understanding of chemistry, of course, engineering, data science, and advanced flow technology. And one of the areas that we see real advantage for this flow technology is in accelerating drug substance development. So you guys are all probably very familiar with this cadence from lead optimization all the way through to commercialization of an active pharmaceutical ingredient. We usually get engaged somewhere around this candidate selection timeline when somebody's picked a molecule and is ready to take that into preclinical studies. And during that time in the development of a drug, before you're convinced that you have something that's therapeutically useful, there's a lot of steps that you need to go through that all require lots of material till you get to this proof of concept line. And about 95% of molecules, more in my experience, but about 95 according to the best data out there, don't make it past this proof of concept. In fact, they prove to be non-efficacious or they're not economically viable or whatnot. But before you get there, you've got to make a lot of material, a number of deliveries. And my batch experience has been that each one of those scale-ups, those 10x scale-ups from that first gram to kilo and kilo to 10 kilos and then up to 100 kilos, is really a new adventure in process development in many cases, particularly for those steps that are rather challenging, either for reasons of mass transport or exothermicity or safety or other issues that are associated with it. And so there's a lot of time spent developing these really complex to scale steps before you get to the point of this proof of concept. And so all of that really is for naught, since most of the molecules won't make it past that point. So we've been looking at continuous manufacturing as a tool actually to get out of this iterative cycle of process development and look at a possibility of doing a single cycle process development where we can do a one-time development of a process using continuous manufacturing technology that will then allow us to meet this demand as it goes through these testings before proof of concept by just running that process longer or numbering up, making a few more of the reactors. And we've had the opportunity to do this now a number of times for a number of programs. And at the heart of it, the reason that we choose to use continuous here is we can design the reactor to fit the chemistry. So for these very sensitive steps, there's a very close relationship between reaction design and reactor design in the overall process development, where we can actually design in the quality of the product as a function of the reactor design. If the reactor is operating properly, then the chemistry will produce the quality of material that's expected. And this is very different from the experience of batch process development, where really the chemistry is designed to fit the reactor, and not just a reactor, but any reactor in the world, the generic bucket, if you will. So during this cycle of process development, before you hit that proof of concept, those steps that are really challenging to scale, that's an opportunity to use continuous manufacturing to ensure product quality. And our approach here is to use platforms. So platforms in the lab that scale to platforms in the plant, the pilot plant facility, that would allow us to rapidly go from a well-understood, well-engineered, small-scale reactor system to a large-scale reactor that can actually deliver the material that's required for clinic. And we're hoping to speed process development by doing this. And so here you have an example of an organometallic reaction where we're taking isopropyl magnesium chloride, lithium chloride, and we're doing a metal halogen exchange with iodochloromethane, and then adding that into a boron and migrating. So this is a very fast reaction. And what's important in these continuous processes, and we're doing this in a tubular reactor, is that the mixing completion time is faster than the half-life of that organometallic reaction. So that the stoichiometry that you intend is the stoichiometry that occurs for every molecule that's in that tube. And we do that using a very old technology called static mixer technology. And what these static mixers do is they reduce the overall or the characteristic diffusion length for any molecule in the system by laminating it into smaller and smaller units. It's not terribly important at the moment, but we're able to characterize these mixers using some very standardized chemistries where the kinetics are well known, and we can characterize mixing completion time as a function of linear velocity through the tube across these static mixers. And these don't look like huge differences, 1.7 millimeter diameter, 3.75, and 6 millimeter diameter. But I can tell you that in a fast reaction, this small one, this one that's in a 16th inch ID tube, can produce hundreds of grams per hour. At 3.75 millimeters, we're producing on the order of kilos per hour of material. And then by the time you get to 6 millimeter tube, we're producing tens of kilos per hour. So for most pharmaceuticals, even at commercial production, this 6 millimeter type diameter would be adequate to supply tens of metric tons per year. And what we've done is we've characterized the characteristic mixing time as a function of linear velocity for each of those. So with respect to mixing, we can translate the results from the laboratory to a more advanced and larger scale pilot, in this case, the 3.75. And then we can introduce that as a module into our system of modules that are going to produce this molecule. And those are feeds and mixers and heat exchangers and residence time units and mixer settlers. And then we can actually design those in silico. So these are 3D representations of those. And then we can go ahead and build those. And these are actually very small systems. This is a standard 8-foot floor mount hood. You see down here the pump modules, and then there's a heat exchanger and static mixer module, and then some resonance time module. And then if we go across to the next 8-foot hood, there's actually a continuous mixer settler here. And this is all controlled by this PLC-based supervisory control and data acquisition system that sits in between this. And what we can do is ship these small reactor systems around the world and execute the processes wherever manufacturing is taking place. And this one is actually located in Devens, Massachusetts at a partner, Johnson Matthey, for this project right now. And there's another one, a twin of it, that's actually in Switzerland at the moment. And they're both producing material for this project on 100 kilo scale. We have other systems that are platformed. Here is a CSTR type platform where we were doing a reactive crystallization that required solids transfer. And so beginning with first principle kinetics and Levenspiel plots here, we can predict what the residence time in each one of these should be and what the fill volume can be. Again, design, test it in our laboratories, and then transfer that process to a plant where, in this case, I think we've made about 40 kilos of an API over time at a contract manufacturing organization in Europe. And we've done this with a number of different reactor types. This is a photochemistry, so this is a 100-watt reactor. That's our lab scale iris photoreactor, and that has nearly identical photophysics to this 5-kilowatt reactor. So Monday you can figure out the chemistry, Tuesday you can make kilos of it using the same process, just scaled up. For the plug flow reactors, we have a similar setup where heat transfer is very important and residence time distribution, and that's been characterized in these two systems, laboratory and production. And then for ozonolysis, a CSTR approach where this bubble reactor is 100 mil fill volume, and it has very similar mass transport properties to this 1 liter version, which can make on the order of kilos per hour of an ozonide, kilos per day of an ozonide. So we became very interested in ring closing metathesis and how could we solve that problem continuously with this scale by model approach, from being able to demonstrate in the laboratory a small scale result that reliably and predictably scales to meaningful amounts of material that could be used in clinic. And this is an example from a paper in 2005 by BI where they were doing this ring closing metathesis. I think these are Hep C type molecules. And anybody who's done any of these ring closing metatheses, in particular on these large scale rings, is aware of this surface area versus volume issue that happens as you go from lab scale up to very large scales, and that your surface area is only growing by a square, but your volume's growing by a cube. So if you have to get rid of ethylene, which is what's happening in this case, that's going to get harder and harder as you go up in scale. And so we were looking for a solution that would scale predictably using very robust, proven technology, ideally, and was intrinsically safe. We knew we'd be removing, a rather hazardous gas, and it would be using organic solvents. So the way that BI had solved this, and frankly, I had solved with other projects that I had done in the past, is they blew nitrogen through the reactor to remove that ethylene as it went up in scale, and that facilitated removal of the ethylene. So in this case, they needed to operate 6,000 liter scale. They actually split that into 3,000 liter vessels and then forced nitrogen through those vessels and exhausted that out to remove the ethylene at a rate of 1,000 liters of nitrogen per hour through that system. So that certainly worked. They were able to scale this process, and it's a technique that I know a number of people have used to scale ring closing metatheses. But each scale up that you do, because of this relationship between area and volume and the shape of vessels and things like that, and stirring in those vessels, mixing as you introduce the nitrogen, that mass transport changes. And so could we get to a technology that very reliably scales using a single principle across scales? And that brought us to evaporation technology. So these are specialized membranes, and the ones that Compact Membrane Systems makes are fluorinated polymers. And these membranes selectively allow very small molecules like gases, in this case ethylene or water is one of the areas that they use it quite a bit. So for drying, to pass through the membrane, but keeping the solvent on the retentate side. And there's a number of driving forces that affect this rate of evaporation, temperature, concentration gradient, vacuum pressure, water activity, all of those scale invariant, and then surface area. And so that's the one that we thought that this was a nice technology to use, because it's something that we could control independent of the size of the reaction that we were going to use. And the format that they make these hollow fibers in goes everything from flat sheets to hollow fiber membranes that can be bundled into very large surface area. And the way they work is the liquid is fed on one side of the membrane, and then either vacuum or a sweep gas is passed through the other side of the membrane to carry away the gas or vapor that's desired to be removed. And this technology is really robust. I think one of the things that really opened my eyes in talking to compact membrane systems is when they told me that the transformers that are out on electric poles actually have these membranes inside to remove water from the oil continuously, and they last for a decade in some cases. So very robust technology. Passive, requires a pump to feed it, but it doesn't have any moving parts of its own. Very robust membranes because they're fluorinated polymers. And so we can do interesting things with them, like dry pass anesiotrope is one of the applications that they used. They do gas separations for different sizes, and they have really good stability towards polar A products, which is often a problem with membranes, is that they tend to have poor organic stability, but these in particular are very stable. And then we were also informed about this by some work that had been done at Pfizer, a really beautiful paper that they did with compact membrane systems, where they needed an anhydrous source of terpbutyl hydrogen peroxide for an alpha hydroxylation of an enolate. And so what they would do is they would extract this 70% aqueous terpbutyl hydroperoxide with nonane, and then pass it through a membrane drying system, the pervaporation membranes. And you can see those here. This was actually done in partnership between Pfizer and ASMChem in ASMChem's labs in China, where they set this up and they were able to pass this extracted wet T-butyl hydroperoxide system through the membranes, get it very dry so that they could then take an enolate of this amide and react it with that terpbutyl hydrogen peroxide and produce the desired product with stereo control. So really interesting application of this technology to remove water. There was another, which is getting closer to our goal, where they're removing water to actually drive reactions. So being able to take geranol and acetic acid in the presence of a lipase and drive that equilibrium reaction to completion by continuous removal of water by recirculating the solution of the reaction solution through this membrane module, removing water, and then driving the equilibrium over towards geranol acetate. And this was done with some collaborators at Kansas State University with compact membrane systems. So based on those two examples, we were attracted to the idea of being able to use it for metathesis as well. As you know, in ring closing metathesis, it's an equilibrium reaction which is driven by the removal of ethylene. But the other thing that Grubbs and coworkers have shown is that ethylene actually leads to decomposition of the metathesis catalyst. These catalysts are typically very stable catalysts. This half-life more than a month at 55 degrees in benzene. But as soon as they add ethylene to that, hydrides are observed in the NMR, and decomposition is off to the races. So if you want to be able to use very low catalyst loadings of these expensive catalysts, removal of ethylene is also an important capability. So what we want to do is use that membrane to replace this system of 3,000 liter vessels that are being sparged continuously, and instead pass it through a membrane. So we looked at the impact of ethylene on this model system to begin with. We wanted to understand, how detrimental is ethylene for this. These were all done in this batch reactor. So if we take and monitor the reaction conversion as a function of time in a nitrogen sparged vessel, much like the BI group ran their process, you can see that we reach maximum 100% conversion very quickly, less than 30 minutes here. If we now seal that vessel with some decent headspace, even that little bit of ethylene that's retained in the headspace already starts to reduce the overall conversion, and it doesn't get any better, which suggests that we've reached equilibrium or the catalyst is decomposed. If we start to pressurize this now with ethylene, 1 atmosphere of ethylene, even worse performance, and then 20 psi of ethylene, we're down in the about 40% conversion, and these are more accurate representations of what we would experience in a flow system. That's at least our expectation. So we moved on to test that idea of what would happen in a flow system, and we did it in 2 different types of tubing: for stainless steel as a coil, and FEP, which is a fluoropolymer coil. And actually FEP has a little bit of permeability to ethylene, and you'll see that play out here. So as we set this up, we mix these to get a homogeneous stream in toluene that then passes through a heated reactor or temperature controlled reactor. In this case, it's held at room temperature. to get our product. We can follow this very easily by NMR. And what we see is we're normally in batch, when we're sparging this, we're at 100% conversion after 30 minutes. No matter how long we let the residence time be in this reactor, we never get greater than 60% conversion. Even in the FEP case where there's some permeability to that membrane, it looks like catalyst is probably decomposed at this point. We're not getting any further conversion. In stainless steel, obviously no permeability, and we're getting even lower overall conversion. So we're not the first to think about how do you do metathesis continuously and see the attractiveness of this. There's been a few other examples in the literature. This one from Fogg in 2010, a rather large ring that they're trying to close, so challenging in its own. Introduce catalyst, fully mixed, and then put that into a vessel, continuously putting it in and taking it out while sparging that vessel with argon. So a CSTR approach, where you've got a homogeneous stream in, where the catalyst is closing this down and producing ethylene, and then argon is being used to carry that ethylene out and then continuously pumping out. Good yields of this, long residence time, and done in a CSTR, a very broad residence time as well, and rather low turnover numbers of that catalyst. So an approach, but still depending on the surface area of a reactor, which eventually you're going to have to scale. So that's something that's still going to be difficult to control. We're still having to sparge a gas through there and deal with a flammable solvent potentially vaporizing into that gas as well. And then this group in Chem Sus Chem in 2014 demonstrated the Teflon AF 2400 tube in tube. So this is a small reactor system that has a tube within a tube. That inner tube is actually made up of this AF 2400, which is a very thin, permeable fluorinated polymer. And you can connect vacuum to the inside of that tube and pull ethylene out of the system that way. Unfortunately, this AF 2400 Teflon is extraordinarily expensive. It's only made in tubular form by one company in the U.S., and it's very fragile tubing, and it's just an extruded tube, so it's hard to figure out how you're going to scale up the surface area there in these tubular membranes, since it doesn't present as a hollow fiber, or you wouldn't want to have to use large sheets. That's difficult to scale. So good conversion, decent turnover numbers, low resonance time based on the permeability of that AF 2400. So a decent solution, but not quite clear how cost effective it would be to scale that and how the engineering would work out. And then finally, you can take the brute force approach, high temperature, high catalyst loading, and get conversion in this product with very low turnover numbers, however. And so this brute force approach was not attractive due to the very low turnover numbers. So in evaporation, and what compact membrane systems has is they have this clamshell reactor that allows you to test out the membranes as a small coupon, and this is also material sparing. So this is CMS's membrane testing platform. What we're going to do is we're going to pass the substrate through one side of this, and you can see it here schematically, where one side it comes up through these holes and goes out through the other side on one side of the membrane. Ethylene's to be transported across that membrane, and then on the other side, we're not pulling vacuum, but we're just sweeping nitrogen through this in an effort to carry away that ethylene. And so coming out this end of it, we expect to have ethylene in our nitrogen, and out this end of it, we expect to find our product. So the first thing we wanted to study was what is the ethylene permeability in these membranes in actual measurements. And so the way we did this is we took ethylene gas and we passed that on the retentate side, and then we actually capped the end of the ethylene of the other side of it, the permeate side, and had that exit out through a bubble flow meter. And in this way, you can test what the ethylene permeability is of this. And more importantly, we can look at that as a function of one of the parameters, temperature in this case. And we can see that as we increase temperature, we increase the ethylene flux across that membrane while maintaining everything else constant temperature, constant pressure, constant feed, constant surface area of that membrane. And so that's a tool that we're going to have to be able to manipulate the removal rate of ethylene. And then the other thing we were interested in was how selective were these membranes? We're going to be in toluene, so we want to know how much toluene is going to be lost to that gas phase. Of course, if we were losing large amounts, like you could imagine you were if you were just bubbling nitrogen through this, then it wouldn't be a very attractive alternative. But what we see is if we set up a mass flow meter on one side of this, on the retentate side, and flow through at 4.33 grams per minute, I'm sorry, this should be 0.4335 grams per minute, not 4.3. If we flow through at that rate and then measure, collect in a vial for a minute and measure how much material comes through in a minute, we can see that irrespective of temperature, we're collecting very close to our intended mass, and the relative difference between what went in and what came out is rather small. And since this is the difference of about a second of collection time, it could even be partially due to human error. So very little of the toluene is going to be lost across this membrane. Now we're working in this flat sheet for purposes of testing. We just were interested in how that flat sheet residence time distribution compared to the coil reactors that we were using. And not surprisingly, this purple line is the residence time distribution. It's quite poor relative to or broad and poor relative to a plug flow reactor. In fact, it looks very much like a single CSTR kind of profile. And the way we did this was, if you're feeding toluene into the reactor, and that clamshell reactor is behind here, we can give it a spike of fluorinone and toluene, and then look at that by UV vis on the backside. So there's a UV vis cell, and so that's a very easy way to measure residence time distribution. And we see that we're going to have a poor residence time distribution. However, for testing purposes, this would give us some parameters that we could then transfer to hollow fiber testing. So going back to our model compound, and with 0.1 mole% of the ruthenium catalyst and holding temperature constant at ambient temperature, in this case at 24 degrees, with a 2.4 mil internal volume. I'll remind you what our batch was. We were nearly complete after 30 minutes in the FEP plug flow reactor. We were at about 60% conversion after about 35 minutes. Now in this case, with the membrane in place, we can get up to much higher conversions here, about 85% or so after 80 minutes residence time. So very long residence time, clearly not practical, but still we're seeing that we can effectively remove ethylene and push these reactions further by using the membrane. We have this other handle to play with, which is temperature. So we know that at higher temperatures, we increase our ethylene flux rate across that membrane. So this is about a 17 square centimeter membrane that's in there. And as we increase temperature, holding residence time constant now at 19 minutes, as we increase temperature from 25 degrees up to 50 degrees, we see greater and greater conversion of the product. At 50 degrees, we're very close to full conversion at 19 minutes of residence time. And we still have room to go. These membranes are quite stable, so we can go up much higher in temperature. And as we pursued further optimization of this, looking at two catalysts here, we were able to identify conditions that get very excellent turnover numbers and very reasonable residence time. So here in entry 6, we're using catalyst 1 at 0.05% loading. And now we've increased the temperature to 120 degrees so that we can really shorten that residence time. We didn't see any effect of the pressure, really, the back pressure on the system, not terribly significant, nor was there a significant effect of nitrogen flow rate on the removal of ethylene. So it doesn't look like we're saturated on the ethylene side. And at a flow of 50 mils per minute, we could get a 5-minute residence time, very high conversion to the product, no starting material left, and decent turnovers, nearly 2,000 turnovers. With this catalyst, we can get even higher turnover numbers, although it's going to take some longer residence time. We only achieved 76% conversion with 24% remaining starting material, but no decomposition, no unintended products. So it looks like we could push this turnover number even further. Of course, we wanted to look at the scope of this reaction. So in each case, and I'll show you a number of cases, we took a substrate that we wanted to perform ring closing metathesis on, and we looked at a number of variables, including substrate concentration, the flow rates or stoichiometries of dying, and residence time, temperature, and total concentration as well, because we're going to do some large rings. So each one of the substrates went through this multi-parameter optimization, and here we can get this Bach dial Bach amide to 90% conversion, or 90% yield, sorry, with complete conversion. And we can extend this to some other substrates, all using the same catalyst. Here's another substrate that we looked at, the 6-membered ring, closing that, going up to a 7-membered ring, and finally an 8-membered ring, all with 90 or better, 89% yield, and then isolated yields are provided next to it. These are assay yields based on internal standards. You do have to go down in concentration as we go to larger rings so that we can maintain the selectivity for the desired product as opposed to cross metathesis products. And in fact, these larger rings actually took a little bit more catalyst loading. And we compared each one of these in the membrane reactor versus just a stainless steel plug flow reactor. In each case, we were rewarded with higher conversion in the membrane reactor. For some of the challenging substrates, this very large ring, we looked at the effect of the different catalysts in this system, and we can see that moving to these nitrogrella catalysts, very active catalysts, we can actually get very good yield and selectivity for the desired ring closing metathesis as opposed to cross metathesis with these nitrogrella catalysts. Getting a very respectable 95% yield with 98% selectivity. And reasonably short residence time, 10.5 minutes. And again, this residence time is somewhat distorted because of the long or the poor residence time distribution in these systems. However, this platform now allows us to determine a surface area impact on ethylene removal and the impact on the chemistry, and knowing that we can move to a hollow fiber format, which will behave more like a plug flow reactor, we can use that data then to linearly scale. And what we were starting on more recently is to actually test this in some of the small scale hollow fibers, which should have more plug flow characteristic. And so what I think we're headed towards here is a laboratory platform that we're going to be able to use our understanding of the residence time distribution, the ethylene flux that's been measured, the surface area that's available to us, the effective temperature. All of those components are being studied in this system and being compared to the performance of the hollow fiber. And that allows for more than 10,000x scale up in going from these membranes to a very small footprint. These columns are about 5 inches in diameter and about 18 inches long, and there's 4 of them in series, so you can put more and more in series. And so that's a very dramatic scale up of a process that typically has been very challenging to scale up. And so in our system of platforms that included plug flow, packed bed, CSTR, the photoreactor, electrochemical reactors for lab and production scale, as well as unit operations, we can now add evaporation for metathesis, and also for some other applications like the one shown by Pfizer or Kansas State with compact membrane systems. So I hope that was interesting to you, and that it was something that you might consider as you look at scaling some of these more complex reactions, such as ring closing metathesis. I'd like to acknowledge again Tim Jamison's lab and Chris Breen in particular, a graduate student there who did most of this work himself, Henna Murin and team down at Compact Membrane Systems that really helped us understand how these membranes work, how to use them, and how to characterize them appropriately, and then provided a number of examples of the membranes. And then the team at Snapdragon. This is an old photo, we're bigger now, but this is the group pre-social distancing days. So thank you very much. I really appreciate the opportunity to present this to you.
Yeah, great. Thank you, Matt. That was awesome. Really love just complete reaction engineering and bringing a tool to a problem that's been persistent in these types of reactions. We'll take just a few questions, just a couple questions, and then we'll turn it over to Tehshik just so we can stay on time. So one question that comes from Donna Blackman. She wanted to see if you could explain what you mean by laminating the reactor.
Yeah. So as the process streams move through these tubular reactors, we're going very slow. So they're in a regime of flow called laminar flow, where the two streams come into the reactor and they just kind of cozy up next to each other and proceed along down the tube. And the only thing that is mixing them is diffusion. They stay separated, and we have some really interesting color coded systems that we can watch that happen in. So what the static mixer does is it actually takes those two streams and it keeps splitting them into finer and finer streams. And so what you have really is like phyllo dough, to take it back to cooking, where you've layered the dough and the flour and the butter into finer and finer laminations. And now the characteristic diffusion length between any piece of flour and any piece of butter, or our two reactants in this case, is much smaller than it was. So now diffusion can mix very rapidly, as opposed to having to go from one side of the tube all the way to the other to meet.
Got it. Yeah, no, and as delicious as phyllo dough is, it's not well mixed, right? The beauty is in how things are separated there. Then one more question that comes from Lawrence Creamer. It comes around since typically ring closing is done on pretty dilute, right, to conditions, right? So how do the conditions that you develop, how do they compare in terms of a traditional RCM where you want to run it dilute so you don't get sort of polymers and dimers and things like that?
Yeah, it's going to be the same. That's not going to be something that we're able to fix by just putting it in a continuous flow reactor. That depends on the selectivity of the catalyst and the kinetics of the two processes, and that's not something that changes. So if you notice, the larger rings were at much higher dilution than the smaller rings.
Yeah, and so basically, how do you deal with this with flow? Like how
Yeah, so the opportunity is that you can recycle solvent continuously. So it's very easy to connect one of these systems to a continuous solvent recycle. And so if you had a system that used hundreds and thousands of liters of DCM to do this ring closing or toluene, we can still use a much smaller amount of solvent in total, because we can continuously recycle that solvent back as part of the integrated system between ring closing metathesis and distillation to recover solvent. So since both of those are running continuously, you can close the loop and just return the solvent to it. So much greater process intensification.
Yeah. Okay, cool. So I would love to take more questions, but I think we need to move on in the interest of time. Matt, if you can open up the chat, I think you may be able to open up the chat while you're listening in to Tehshik, and you might be able to just type in answers. There's a couple more questions. I have great questions, by the way, and thanks everybody for listening and also typing in a question for the speaker. I'm going to turn it over to Steve. He's going to introduce Tehshik, but thanks again, Matt. Appreciate it.
All right. Hi, everyone, and special thanks to Nick Schiaffini for asking when the Silverman-Hanson Comedy Hour is starting at future ACS meetings. Probably
yeah,
not.
I'm keeping my day job, Steve. I don't know about you, but I might have a tight 5, but that's it.
We were discussing maybe a bit that showed our old organic chemistry exams. So if anybody wants to see our old exams, maybe that'll come next time.
That's a little
All right.
scary.
So, I'm really excited that we finally got Tehshik to do one of these. Thank you very much, Tehshik. That Tehshik's a very strong contributor to a lot of DOC activities. So again, thanks for agreeing to this. It's a real pleasure to introduce Professor Tehshik Yoon from the University of Wisconsin-Madison. Tehshik started his chemistry education at Harvard, working for Dave Evans. After a master's with Eric Carrera and a PhD with Dave McMillan in his first class at Caltech and then Berkeley, Tehshik returned to Harvard as a postdoc with Eric Jacobson and working on asymmetric catalysis with chiral ureas. In 2005, Tehshik joined the faculty of the University of Wisconsin-Madison and rose through the ranks where he's currently a full professor. His group is interested in the use of open-shelled reactive intermediates in organic synthesis, and he's made many really impressive contributions in the area of photoredox catalysis and demonstrated some really beautiful photocatalytic cycle additions. Tehshik has a long list of awards. Some of the most recent include the Frederick Wilhelm Basel Award and the ACS Teva Pharmaceuticals Scholar, and of course the Cope Scholar Award last year. Today he'll talk about stereo control and photochemical synthesis. So I'll turn it over to you, Tehshik.
Great, thanks. Let's see. I need to share my screen and then get this going. All right, can everyone see this? All right, super. So thanks very much for the invitation. I have really enjoyed the DOC symposia that I've seen so far, up to and including the Hanson Silverman Comedy Hour, so thank you very much for that. Okay, so since this is a little bit of an odd situation for all of us, I thought I'd give an unusual talk. This is not a talk that I've given very often. I think I've only actually given versions of this science a couple of times now. And the reason that I wanted to give this talk is because I've been doing a lot of reflecting while I've been working from home. And I've been thinking a lot about what it is that, how it is that we sort of come up with different ideas, what sorts of problems we're attracted to. And what strikes me is that there's a lot of common wisdom that we tend to use when we're developing projects. In total synthesis, this wisdom includes things like, the more nitrogens there are in your total synthesis, the longer the synthesis will take. In asymmetric catalysis, we'll often talk about C2 symmetry being really important for catalyst designs and so forth. And these are rules that have kind of grown up organically over years and years of experience of multiple scientists, but they are only common wisdom. And so I wanted to tell you a story about how my group has been coming to realize that a lot of the common wisdom around the design of stereo-controlled photochemical reactions needs to be re-examined. So the story that I'm going to tell you is conducted by this team of people in my group. A lot of the work that I'll be telling you about today has been done by the people on top row here. It was started by Kaz Scooby, who was a graduate student in my group and is now about to start his independent career at Skidmore College. Jesse Kidd is a graduate student in my group. Jian Zheng was a postdoc in my lab, and Wes Swords was a postdoc in my lab as well. And I also am going to tell you a little bit about the computational work that my collaborators at KAIST have done. Quentin Jung was the student who led that effort. Okay, so when I first started working in my independent career in 2005, the problem of asymmetric stereo control in photochemical reactions was essentially an unsolved one, and not for lack of trying. The first experiments in asymmetric photochemistry date back to the 1930s. So it's been a really long time that chemists have been trying to control the stereochemistry of photochemical reactions. So the common wisdom for why this was so difficult you'll find all over the photochemical literature, but it's really highlighted in this section that I've put in blue here. What you'll find is this idea that when you photoexcite an organic molecule with light, you generate these really highly energetic intermediates that are so reactive that it's difficult for catalysts to control what it is they want to do. So this is really a statement of the so-called reactivity selectivity principle. The more reactive something is, the harder it is to control its selectivity. But by this point in modern synthetic organic chemistry, there are so many examples of exquisitely selective organic reactions involving very reactive intermediates that we know that there's nothing intrinsic about the reactivity of high energy intermediates that makes them impossible to control. So early on, when my group started working on this problem, this is really the analysis that we made, that when you try to control the stereochemistry of a thermal reaction, something that's not photochemically activated, then an analysis goes something like this. There's some starting material that goes over an intrinsic barrier to give you a product of interest. And a catalyst operates by offering the reagents a lower energy pathway that gets to the products faster. And if this catalyst is chiral or has some other elements of control associated with it, can really control all of the various outcomes of this reaction, including the stereochemistry. So this really is how all of modern catalysis works. In asymmetric photocatalysis, however, The first step of a photochemical reaction is distinctive in the sense that a photon of light pumps a molecule up from the ground state to the excited state. And so these excited states are so high in energy, 60 to 80 kilocalories per mole above the ground state, if these intermediates really want to do something, they can relax quickly to the ground state on the order of picoseconds or nanoseconds. And so in order for these intermediates to undergo some reaction, the intrinsic barrier by which they react needs to be relatively fast. And so catalysts have a hard time intercepting these fleeting intermediates and controlling what it is that they do, or at least controlling them so that they're significantly faster than the direct photoreactions. And this is important in asymmetric catalysis because in order to control the stereochemistry of a catalytic reaction, you really need for two things to be the case. First, of course, is that you need a chiral catalyst to bind reversibly to a starting material and then control the stereochemistry of the subsequent transformation. I think it's pretty obvious. I think everybody who works in this field pretty much has a good intuition for this fact. But equally important is the fact that the catalytic reaction has to be a lot faster than the background reaction. If there's any background reaction that can also give product, then the overall enantiopurity of the product that you isolate from this overall process is a superposition of the rate at which the product is being formed by the stereoselective pathway, and the enantioselectivity is diminished by the participation of any of this racemic pathway. Now, for the Diels-Alder reaction that I show you on this slide, that background reaction isn't really a problem because chiral Lewis acid or Bronsted acid or organocatalysts can increase the rate of the Diels-Alder reaction by an order of magnitude or more. And so you really don't have to worry about the participation of this racemic background pathway. But for photochemical processes, if the intrinsic rate of these direct photochemical processes is very, very fast, then you need to design catalytic strategies to ensure that the rate of the process when the substrate is bound to a chiral catalyst is significantly faster. And this was really the piece that had been missing from asymmetric catalytic photochemistry for most of the history of the development of this field. The first person to kind of start thinking about strategies for making this catalytic stereoselective pathway a lot faster than the direct racemic background photoreaction was Mike Crochet. And there's this paper that I don't think really gets cited enough. It's this lovely JOC paper in 2003, where Crochet designed a hydrogen bonding acceptor that was chiral and covalently attached to an organic photosensitizer. So the strength of this binding interaction was reasonably strong. And then when this complex absorbed a photon of light in this photosensitizer, that photosensitizer was proximal to the organic substrate, such that the excited state was born in the chiral environment of the receptor. And so the enantioselectivity could be influenced by the chirality of this organic photosensitizer. So the enantioselectivities are modest, but this was the first example of really true catalysis of an asymmetric photoreaction, where the enantioselectivity shows that you're essentially outcompeting the racemic background reaction. So this is the strategy that everyone who's worked in this field since this point has used to some degree or another, having some kind of pre-association between an achiral substrate and a chiral catalyst. And the state of the art is really this beautiful chemistry that Thorsten Bach's group at the Technical University of Munich has been working on for the last decade and a half, where, again, it's a chiral hydrogen bonding motif that is covalently attached to an organic photosensitizer. And the design of this is such that the hydrogen bonding pattern of the lactam in the catalyst and of the amide moiety of this quinolone are complementary, which orients the substrate such that first, the energy transfer between the sensitizer and the substrate can be really fast because they're physically very close in space. But more importantly, the directionality of the hydrogen bond ensures that this double bond has one face that's exposed to solvent and one face that's blocked by the photosensitizer. And so cycloaddition can only happen from one face and deliver you really good enantioselectivities. So this is really beautiful work. I think that if you were to assign a criticism to it, however, you'd note that the rates of these reactions are relatively slow. And so consequently, the catalyst loadings tend to be relatively high. And this is pretty true across the board for asymmetric photochemistry. For the successful examples where enantioselectivities are high, the loadings of the chiral catalysts tend to be 10, 20, 30 mole percent, which is good for a problem that's this difficult, but nevertheless is still a lot higher than, let's say, other technologies in non-photochemical reactions. So for the past several years, my group has been trying to make the argument that transitional metal photocatalysts of this sort, that are now well appreciated to be excellent photoredox catalysts, are also really excellent triplet sensitizers as well, and can behave and do all of the same chemistry as classical organic sensitizers like benzophenones and thiazanthones. And there are a lot of properties that are different between the two of them. Some of them are trivial. So for instance, it's much easier to tune the structure of these iridium complexes and maintain good photoactivity than it is for an organic photosensitizer. They're also a lot more chemically stable than small organic molecules. But the big difference between these two, I think I would have to argue, is the lifetime. I mentioned that the excited state of an organic molecule typically has a lifetime on the nanosecond kind of time scale. But these transition metal complexes have excited states that are several orders of magnitude longer. And in bimolecular organic photochemistry, this excited state lifetime is everything. The longer the excited state lives, the higher probability it has that that excited state can interact with another molecule before it relaxes to the ground state and sort of loses the energy of that photon. So when we've done head-to-head comparisons of triplet sensitization reactions that can occur using either of these two catalysts, we find that the efficiency of the reactions with these iridium photocatalysts tends to be significantly higher. And so the strategy basically was this. Could we take the designs that people like Thorsten Bach have been using to design highly enantioselective photocatalysts and embed a transition metal photosensitizer in it to couple the high enantioselectivity that's derived from these sorts of catalysts with the excellent photophysical properties of these iridium catalysts? One more point that I'll make is that these diaryl ketones that are the go-to photosensitizers in organic photochemistry, they're flat. They typically have no stereochemistry associated with them. But these octahedral transition metal complexes are often chiral. And so they've got helical chirality. I'll point out the work of Eric Meggers, who for the past several years has really been showing that you can synthesize enantiopure iridium, osmium, and rhodium complexes and use them in a variety of asymmetric processes as Lewis acids, as hydrogen bond donors, and recently also as photoredox catalysts. So our strategy looks something like this. Could we take the design principles from Thorsten Bach's approach and replace the organic photosensitizer with a transition metal photosensitizer? And can we also modify the structure of these iridium photosensitizers with hydrogen bonding motifs that can bind and recruit an organic substrate proximal to the chiral stereocenter defined by this transition metal complex? So right off the bat, this was the design that Kaz came up with. We know that in these iridium complexes, the cyclometalating ligands have a big impact on the triplet energy of the photosensitizers. And in particular, when you put these electron withdrawing groups at the periphery of the cyclometalating ligand, then you have a very high triplet energy. Second, we also knew that the L2 type ligand has less of an effect on the excited state triplet energy, and you can really do a lot to change the structures of them without really perturbing the photophysics of the complexes. And so we installed this hydrogen bonding motif. It was a motif that Meggers had used as an organocatalytic hydrogen bonding motif in some of his chiral iridium ground state catalysts. And so we knew that this could interact with a substrate that looked something like this. And so right off the bat, we were getting some reasonable enantioselectivities. The fact that a hydrogen bond was important is consistent with the fact that the enantioselectivities are higher as you go to less polar solvents. And at low temperatures, we're really starting to get some measurable enantioselectivities out of these reactions. Again, consistent with the fact that a hydrogen bond is important, this is the substrate that we screened on. If you block this NH bond, the reaction works just fine, consistent with the fact that there's still triplet sensitization occurring. But if you disrupt the hydrogen bond, there's no enantioselectivity in all of these processes. Okay, so what does this hydrogen bond look like? we had imagined that it might look something like this, that this amide could be complementary to the amide of the quinolone. And so maybe if we were to tune the Lewis basicity of this carbonyl, we might be able to change the binding and change the enantioselectivity selectivity. So that's true. If we change the basicity of this amide, we can change the enantioselectivity selectivity. But then the one control too many shows that actually we don't need the carbonyl at all. So this bonding motif is not correct. This is not how the catalyst is interacting with the substrate. Okay, so well then we decided that maybe what was happening is that the bi-identity hydrogen bonding interaction looks something like this, that this NH bond is pointing here, this NH bond is pointing here. And so maybe what we can do is change the Lewis basicity of this nitrogen lone pair and improve the enantioselectivity selectivity. And again, if we change the nitrogen to a sulfur, we get a little bit of an increase in the enantioselectivity selectivity. But again, one control too many. If we delete that heteroatom altogether, we get the highest enantioselectivities selectivities. And in fact, this pyridyl-pyrazole turns out to be the optimal ligand for this catalyst. And more importantly, this pyrazole is the important part here. If we get rid of the pyridine, the reaction is a little bit slower, but nevertheless, the enantioselectivity selectivity is still good. But if we block this NH bond, then there's no enantioselectivity selectivity whatsoever. Okay, so by this point, we had a reasonably good enantioselectivity selectivity, but we had no idea how exactly this catalyst was working or what this binding interaction might look like. We did know that this NH was critical and there was some kind of hydrogen bonding interaction occurring, because if we did a titration experiment where we took this photocatalyst and we began adding in more and more of the quinolone substrate in the NMR, we could observe the change of the chemical shift of this NH group. And we could fit it to an isotherm that models a one-to-one binding interaction and calculate with a very good match a binding association constant of about 500. Which is not incredibly strong, but it is strong enough to say that at the initial concentrations of this photoreaction, roughly 85% of the catalyst is bound by this substrate. So one question we asked was whether or not we could figure out how to improve the binding of the substrate to the catalyst. So what Kaz noticed as he was doing this, this binding interaction, of course, the chemical shift of this NH changed significantly because it's involved in hydrogen bonding to the substrate in some way. But he was doing the measurement on a high field NMR, 600 megahertz NMR, and he was actually able to see pretty much everything across the board. So there's, he could assign what all of these different chemical shifts are, and some of them didn't really change very much as you added more and more of the substrate, but some of them changed really significantly. And so after assigning all of these peaks, Kaz made the assumption that the peaks that change the most are the ones that are most intimately involved in the binding interaction with the substrate. And so we built a heat map that looks something like this. In red, these are the resonances that have the largest change in chemical shift, followed by the ones in blue, followed by the ones in green. And what you'll notice is, first of all, the ones in black don't really change all that much. I'd mentioned we can delete this pyridine altogether, and indeed, we really see no significant change in the chemical shifts if you start looking at the chemical shifts and start adding in some of the substrate here. Interestingly, however, some of the largest chemical shift differences are over here on this ring that, at least in the way that we've drawn this catalyst, is far away from presumably where the substrate is binding. And when we looked at this heat map, of course, this made sense. This is a three-dimensional object, and so this NH bond is actually pointing at one of these cyclometylating ligands and not at the other one. And so what we really ought to be doing is changing the structure of this kind of a ligand. So after a little bit more optimization, what we found is that by changing the pattern of fluorination from this to this, we can increase the enantioselectivity selectivity of the reaction and concomitantly also increase the association constant by a couple of orders of magnitude. So this is the optimal catalyst. I'll show you the scope of the reaction. You know, this is really sort of a concept piece, so I'm not going to really focus on the scope too much, except to point out that consistent with the fact that hydrogen bonding seems to be important, if we put in large functional groups proximal to the putative site of hydrogen bonding, then we disrupt this binding interaction and the enantioselectivity selectivity is lower. Nevertheless, we can rescue that enantioselectivity selectivity by using a smaller group here rather than the larger chlorine. So to understand how exactly these two, the catalyst and substrate were binding, we turned to computations in collaboration with Mookie Bake's group. Huimin Zheng was the student who came to my lab and spent a semester to really work all of this chemistry out. And what he proposed was interesting. There's this really unusual hydrogen bonding interaction, where the primary interaction is the hydrogen bond from the pyrazole to the oxygen of the quinolone. But then there's a secondary hydrogen bond between this NH group and either the lone pair on this nitrogen or the electron-rich pi cloud above this pyrazole, we're not entirely sure exactly which, that orients the substrate such that it's directly over the cyclometylating ligand where the exciton lives, so that triple energy transfer happens really rapidly through space, and also blocks one face of the olefin, so the cycloaddition has to come from the other face, giving you good enantioselectivities. And this immediately shows you both why you need to have this NH bond for good enantioselectivity, and also why a really large group in this position would disrupt the binding interaction and give you lower enantioselectivities. So all of this seems to make sense. Since NMR was such a great tool for us to optimize this reaction, I'm going to show you one more thing that we did really briefly. We decided that it would be cool if we could use the NMR as a tool to look at the dynamics of these reactions as well. So in collaboration with Heike Hofstetter, who is the associate director of our NMR facility, Kaz designed a photoreactor where we use a fiber optic to pump LED light that's controlled by the NMR console through this fiber optic into the bore of the magnet and deliver the light in a controllable way into the reaction volume, so we can actually look at the reaction in real time. And this is good for really fast photo reactions. I'm showing you some of the traces here. This reaction here is done in about 2 minutes. And nevertheless, because we are doing in situ NMR, we can still get good kinetic data within those 2 minutes of time. So doing so, what we find is that this photoreaction is first order in the photocatalyst. It shows saturation kinetics in the substrate and shows sort of first order dependence on the concentration of light, the photon flux. And so this is consistent with the model where there's a ground state interaction between the catalyst and the substrate. And as soon as you irradiate it, the reaction takes off. So all of that seems to make a lot of sense. Okay, where I wanted to finish up was the really surprising piece here. Which is that, Jian was a postdoc in my lab who wanted to develop an intermolecular version of this reaction. And after doing a little bit of modification, this catalyst is a little bit different. It's got a different fluorination pattern, a slightly different L2 ligand. He could get good enantioselectivities for this crossed intermolecular 2+2 cycloaddition reaction. But there were some interesting differences in the scope. So for instance, I mentioned that the enantioselectivity is a lot lower when you put something next to the site of hydrogen bonding. And that's also true here, but the enantioselectivity was not rescued by putting in a smaller group. More interestingly, if you block this NH group, which we said was critical for orientation of the substrate, the enantioselectivity is still pretty good. So something seemed really different. One thing we wondered was, whether or not it was the other substrate that was binding to the photocatalyst rather than the quinolone. There is, after all, this NH bond that could still interact in a sort of similar way with this quinolone. But that didn't really seem to pan out with some of the scope here, where we don't necessarily need that NH bond. And more importantly, when we look at the binding interactions by NMR, it's clear that the quinolone still binds at least an order of magnitude more tightly than the maleimide does. You can also see that in the kinetics. The reaction is first order in the photocatalyst. You see saturation kinetics in the quinolone and still first order in maleimide. So all of this seems to indicate that we still have a resting state where the catalyst binds the quinolone. And then there is the rate determining step is a reaction that involves the maleimide reacting with the catalyst and forming product. So clearly we're still binding the quinolone. But if we look at the rate at which the photocatalyst interacts with the maleimide or the quinolone, these are Sternblumer studies here that show that the maleimide reacts significantly faster with the excited state photocatalyst than does, the maleimide reacts significantly faster than does the quinolone. In fact, the quinolone really doesn't quench very rapidly at all. You get the same conclusion from transient absorption spectroscopy. The lifetime of the excited state photocatalyst is basically superimposable either in the presence or the absence of the quinolone, but you add the same amount of the maleimide, and there's a significant change in the lifetime. And so what that's telling you is that even though the ground state of this catalyst rests as the complex with the quinolone, that this excited state photocatalyst would rather donate its energy to the maleimide, which is not bound, than to the quinolone, which is right there directly attached to the sensitizer, which seems really strange. And so that was really strange. So again, computation was what really explained this to us. Lemon was able to find exactly that same structure that I'd shown you earlier for the intramolecular reaction. But what he found is that this was no longer the lowest energy conformation. That in fact, a second interaction where instead of having this unusual bifurcated hydrogen bond, there was a different 2-point hydrogen bond between this NH and both of these oxygens that was significantly lower in energy. And if you look at the way that this pi system is oriented relative to the cyclometylating ligand where the exciton lives, it's pointed far away. And if it's pointed far away, there's no pi-pi overlap and there can be no electronic communication. And so the rate of energy transfer from the photocatalyst to the bound substrate is slow because the substrate is held in an orientation where it can't accept triplet energy, which means that the energy transfer has to be a lot faster in an intermolecular fashion, where this maleimide can approach from essentially any vector towards this photocatalyst. So essentially what we're proposing is this, that the ground state quinolone iridium complex is photoexcited. Intramolecular energy transfer can't occur, but the lifetime of this iridium is long enough that rather it would interact with the maleimide, and the maleimide accepts the triple energy, but then has to rebound and react more rapidly with the substrate that sensitized it, rather than escaping into the cage where it could react freely with other solvents. And so we're calling this a triplet rebound mechanism, an analogy to a radical rebound mechanism, where the triple energy is passed to a non-covalently bound substrate, and then it reacts back with the chiral catalyst. So this is a little bit surprising to us because, I started this talk saying that basically for the last decade and a half, everyone who's been working in the field of asymmetric photocatalysis has been designing catalysts that will bind the substrate that gets photoexcited such that as soon as it's formed, it's already directly bound to the chiral source of information. Well, here's an example where that excited state intermediate is actually not bound to the catalyst. And so I think what that's telling us is that this rule of thumb that we had about how you design these catalysts really isn't as rigorously true as even my group thought it was. So what I would say is that these studies show us that there is a benefit to design these iridium photocatalysts that have superior photophysical properties. We can drop down the concentrations of these chiral iridium photosensitizers up to 2 orders of magnitude lower in concentration than analogous organic photosensitizers and still get really good enantioselectivities activities. But more importantly, that the mechanisms of these processes can change really dramatically with just subtle changes in the conditions that you use. And so it's relatively early in the history of the development of the field of asymmetric photochemistry. And I think that a lot of these rules of thumb that we all use to design reactions need to be re-examined. And there's still a significant role that the study of mechanism has to play in the development of this field. Okay, so this is the team of people that I get to work with at Wisconsin. There's a team of about 4 or 5 people in the group who are working on this chiral iridium process. I mentioned my collaborators at KAIST, Mookie Baek and Huimin Zheng. I also have to point out that a lot of this last story was driven by transient absorption spectroscopy. Jerry Myers, our collaborator at UNC, who lets us do transient absorption spectroscopy, and Wes Swords here, who's now a postdoc in my lab, was actually a graduate student with Jerry, so he's the key player there. So that's the story I had to tell you. One more thing that I'll mention really briefly is that starting in June, there's going to be a series of photochemistry spotlight symposia where a lot of us are going to be leading discussions on big questions in photochemistry. And the question that my session will be focusing on is the question of whether or not we understand the mechanisms of photoredox catalysis. So if you'd like to learn more about the issues that I brought up here, there'll be another opportunity to talk about these questions there. So thanks again. I'm happy to answer any questions.
Great. Thank you, Tehshik. I think we're Steve. You want to lead the Q&A? I think we had a few questions online.
Yeah, looks like there's a number of questions. So Nick Champini asks or says, excellent talk session. Do you see similar quenching trends with N-substituted maleimides or maleic anhydrides?
So the question is, do we see the same quenching interactions with some of these other substrates? So these N-substituted maleimides and other, this fumarate. We didn't look at the quenching interactions with these substrates, but we did look at this fumarate, which is so different from the maleimide, and it's similar. The fumarate quenches the excited state of the photocatalyst significantly faster than the quinolone. Essentially, what I'm showing in this in these data is that there really is no quenching by the quinolone at all. If there's a photoreaction, it can't be the quinolone that's responsible for that quenching. That's a good question.
Nick Oniska asks, does the H bonding of the quinolone to the ligand affect the triplet energy or other photophysical properties of the complex?
Right, so the question basically is, once we make that hydrogen bonding interaction between this NH and presumably the quinolone, does it change the way that the photosensitizer reacts? So that's a little hard to say, right? Because we haven't done a complete characterization of everything that the photosensitizer can do when it binds the substrate. But I don't think that that impact is particularly strong. You'd think that if there was an interaction between the quinolone and the catalyst that perturbed its, let's say, triple energy, it would change everything else, up to and including its lifetime. And in this case, as we add, up to, what is this, 100 times as much of the quinolone as there is the photocatalyst, the lifetimes are exactly the same. So I think the perturbation is really minimal. And the way that we think about this is that this L2 ligand really doesn't electronically communicate very much with the iridium complex. And when you're hydrogen bonding something to the NH pyrazole, you're really not perturbing very much about where the photochemistry is really happening. So our interpretation here is that the hydrogen bonding interaction is the outer sphere hydrogen bonding interaction is a small enough perturbation that the effects on the photophysics of the catalyst are not particularly pronounced.
All right. Okay, so Jake Greenwood asks, do you see any homocoupling of the maleimide in the intermolecular 2+2? If not, does selectivity come from proximity after the maleimide is excited?
Good question. Yeah, so we have a hard time seeing the dimer of this maleimide, and a lot of that simply has to do with the fact that there are a couple of things. One is that it's insoluble in toluene, so it kind of crashes out of the solution. Moreover, if it were there in the solution, there's basically 2 peaks in the NMR that you'd look for, so that would be a little hard to see. What we were able to find and isolate was the dimer of the N-methyl maleimide. So it is being formed, but it's not formed to a really significant degree. So I think that's consistent with the mechanism that I drew here, that essentially all of the reaction is happening within the solvent cage. And to the extent that the triplet maleimide is escaping from the solvent cage, that triplet maleimide is able to dimerize faster than it can react with free quinolone. So it doesn't reduce the enantioselectivity activity of the overall process.
Okay. Let's see. Ethan Wapp says, asks if triplet quenching is no longer occurring with quinolone, can you begin truncating this structure?
So I guess that means truncating the structure of the quinolone substrate. Truncating the structure of the catalyst would be difficult because every part of this is responsible for its sort of photophysical properties. We have tried to look at substrates that don't have this kind of NH hydrogen bonding motif, and we're not quite ready to talk about it yet, but there are a lot of other structures that look nothing at all like this quinolone that still bind to the substrate and that will participate in highly enantioselective photoreactions. The really simple modification that I think you might be thinking about is where we delete this benzene ring. And I'm trying to remember what happens there. Jesse ran the reaction. Now I can't remember the results. I think that it worked, but we didn't get good enantioselectivity, if I recall correctly. He's on Slack. I'll see if he's got an answer for us.
Okay, but I think we are rapidly at the end of our time here, Tehshik. Though I appreciate the fact that you're pulling up the Slack to get an answer. But I think we want to thank you and Matt and for presenting today. It was great talk. I love the NMR stuff. I have probably lots of questions about how you get data collection so quick, but we'll save that for another time. And then lastly, I want to thank everybody at the CCHF Center, Emory, Rio and Denise are the people behind the scenes, as well as all the folks at the DOC, especially our webmasters, Brian and Joe. And thank all of you for tuning in. Again, please reach out to us on Twitter. And we'd love to hear from you, love to hear what you'd like, what you don't like, if there's speakers you want to see, or if you would like, us to just refrain from our really lame, dorky chemistry comedy. I don't even know if it's comedy. I think that's a stretch. So, but stay safe, everybody, and we'll see you in a little while. All right.
Thanks, everybody.
Awesome. Thank you, guys.
All right.
Thanks. That was a lot of fun.
Thanks a lot.
Take care.
Thanks for doing this, Tehshik.
Okay. See you later.